Hello viewers, you're welcome to my channel. In this video lesson, I'm going to explain a very important topic which cuts across and forms the basis of every other topic you find in physics, and the topic is measurement and unit. So in the course of this video lesson, I'm going to explain this topic, measurement and unit, under the following outline. So I'll begin this video lesson by giving you a definition, an explanation of measurement, and after which we'll look at physical quantities, and lastly we are going to look at the types of physical quantities, which are the fundamental quantities and the derived quantities. Now, what is measurement? Measurement is simply defined as the process of estimating the size of any physical quantity. Now, this definition might seem complex, but let me break it down and explain. So I'll begin by defining physical quantities. Now, what are physical quantities? Physical quantities are simply properties that are measurable and can be quantified. What does it mean? It means those things that you can measure, number one. Secondly, you can quantify them in the sense that you can tell that, okay, this is 50 of this particular stuff, this is 20, this is 30, or this is 100. So in essence, anything that can be measured and also can be quantified is a physical quantity. For example, you can tell 3 students to go to a football pitch. Let's say we have a football pitch like this, and then tell them to measure the length of this football pitch. So because we can measure the length and also we can quantify it by saying, oh, this pitch is 50 meters. So this is a quantity. Because we can quantify such property, which is length, we therefore call length a physical quantity. Then for those things that, oh, you can't quantify, for example, joy or happiness. Okay, somebody might be very, very happy, somebody might be very, very sad, but we can't tell that, okay, the sadness is up to this unit or this particular quantity. So for such things, we don't call them physical quantity. But what you can simply measure, for example, length, and you can also quantify it, is called physical quantity. Or let's say 2 persons are running a race, we can measure the time they spend running that race. So because we can measure it and also quantify it by saying, oh, Mr. A ran the race for 50 seconds, Mr. B ran the race for 20 seconds. So such a quantity like time is a physical quantity. So also in measurement, another key thing we have here is estimating. Now, what is estimate? So estimation is simply giving a value that is not the actual value, but it is close. It's just like you want to do a particular task. You can say that, okay, I should spend 50 seconds or 50 minutes doing this task. But at the end of the day, let's say you want to wash your clothes. You can say, okay, I should cover this clothes, or I should wash this entire clothes in the next 1 hour. But it is very possible that you might end up spending, so you have decided that, okay, you spend 1 hour in watching that clothes. But at the end of the day, you might end up spending 1 hour 30 minutes. So this 1 hour 30 minutes is the true time spent. This is the true value. But the 1 hour that you gave is just an estimate. So estimate values are values that are not the true values, but they are close to that particular value. Or just like you want to go on a trip and you feel like, oh, on this trip I'm going to spend $100. So you decide that, oh, on this trip you are going to spend $100. But it's very possible that while you are going on that trip, you might spend less. You might end up spending an $80, or you can end up spending $120. So that money you've spent is the true value, but the value you have given to be close is what we call an estimate value. Now, what is different between the estimate and the true value? So bringing it down to measurement, in measurement you only give an estimate value of that particular size. Why is it so? If this is a football pitch, let's say this is a football pitch A, I tell 3 students to measure the length of this football pitch. 1 student can come and tell me that this football pitch is 6.0 meter. Another will tell me it is 6.1 meter. Another will tell me it is 6.2 meter. They won't give me the same value because of the concept of estimate, because it is not actually possible to give me the true or the real value of a particular physical quantity in reality or in life. So by way of concluding, measurement again is the process of estimating, because we can't give the true value. So we are estimating the size of any physical quantity, that is anything that can be measured and then quantified. We are going to look at some examples like length, which can be measured and quantified, then time, then mass, then we talk about it like electric current and a whole lot of others. Now moving on, there's something you ought to know. Every measurement in physics consists of a magnitude and then a unit. For every measurement you do in physics, it is ideal you give that measurement a magnitude and a unit. So if I measure a football field, I will tell that, oh, the length of this football field is 50 meter. This is the magnitude, 50, that's the size, and then meter is the unit. If I come and tell you just 50, it actually makes no sense, because 50 can be used for a whole lot of other things. It can be 50 meter, it can be 50 seconds, it can be 50 kilogram. So when I add a unit, it makes more sense. So if I tell you 50 kilogram, you actually know I'm referring to mass. But if I tell you 50 seconds, you know I'm talking about time. Or if I tell you 50 meter, you know I'm talking about length. So every measurement that is done in physics should be accompanied by magnitude and also a unit. For example, 10 kilometer, where 10 is the magnitude and kilometer is the unit. Now, physical quantities, as I've defined earlier, are measurable properties of object or a system, that can be quantified by measurement. In essence, you can measure them or you can quantify them, giving them magnitude and numbers. For example, 10 kilometer for length or 50 kilogram for mass. So those properties that I can measure are what we call physical quantities. I've given you a whole lot of examples like length, like mass, like time, like electric current, which we'll look at in subsequent parts of this video. So they are not abstract. It's not something like joy or happiness or sadness or hatred. We cannot quantify or we can't measure. We just know that, oh, this person is sad, but I can't tell that the degree of sadness is up to this level or it is greater or less than a particular value. So whatever you can quantify and measure becomes a physical quantity. Now, physical quantities are generally divided into two. We have what we call our fundamental quantities and we have what we call the derived quantity. Now, we begin with the first one, which is fundamental quantity. Now, when you have the word fundamental, what comes to your mind? Fundamental just means the basics or like the foundation. You know, when you want to build a house, you must lay a foundation. So it is on that foundation every other structure will rest on. The beam, the pillars, the roof, the wall, the doors, the windows, and every other thing, they all rest on the foundation. So that's why we call the fundamental quantity the basic, or what, the building blocks. You know, they are building blocks that children do play with to create bigger structures. So now, by way of definition, fundamental quantities, they are physical quantities upon which other quantities are derived or gotten from. So fundamental quantities, they are just a basic quantities. So from fundamental quantities, you cannot get other quantities which we call derived quantities. So in physics, there are basically 7 in numbers. So we are going to move on to look at these fundamental quantities. Here is a table showing the various fundamental quantities we have in physics, their SI unit as well as other units. Recall that fundamental quantities are the basic quantities from which other quantities are derived or gotten from, or simply put, they are the basic or the building blocks for other physical quantities. And there are 7 physical quantities in physics, and they are mass, we have length, we have time, electric current, amount of a substance, absolute temperature, and luminous intensity, which you can also refer to as brightness. So how bright a light source is what we refer to as luminous intensity. And then we have SI unit. SI is gotten from the French word, which is Système International de Units. So it means International System for Unit. So basically, International System for Unit is just a unit which various scientific bodies across various countries in the world have agreed to use for measuring or quantifying a particular quantity. So they have come together and agreed that, okay, for mass, let's use kilogram. So probably before now, country A can say, oh, I want to measure mass with milligram. Country B can decide to use centigram. Country C can decide to use kilogram. But they have all come together and says, oh, there's no need for this difference. Let's just agree on something and use that particular unit. So the unit that has been agreed upon is what we refer to as SI unit. So if I leave country A and go to country B, and in country A I measure something as 50 kilogram, if I go to country B, 50 kilogram will also stand as 50 kilogram. If I leave country B and go to country C and I take this particular substance for 50 kilogram, it's still going to remain 50 kilogram in country C. So it is a system that has been agreed upon by various scientific bodies in the world to use. So for mass, it is measured in kilogram, and the symbol or the representation is kg, big letter K and small letter G. For length, it is measured in meters. For time, in seconds. For electric current, in ampere. For amount of a substance, which is commonly used in chemistry, is measured in mole. Then for absolute temperature, is measured in Kelvin. And for luminous intensity, which I said we also call brightness, is represented in or is measured with candela. Then the other units which are often used, like for mass, it can measure in milligram, that's mg. It can measure in centigram, cg. We can also measure length with kilometer, big K and small m, or centimeter. Also for time, can measure in minutes, in hours, in days, even in weeks, months, years. Then for electric current, the SI unit is ampere, but can measure in what we call coulombs per seconds, which we'll look at when we start deriving unit. Then for amount of a substance, is basically measured in mole. Then for absolute temperature, is measured in Kelvin, but other forms of temperature, which is not absolute, are measured in what we call Celsius, or we can rightly say degrees Celsius, or Fahrenheit, which you can rightly say degree Fahrenheit. So other forms of temperature can be measured in degrees Celsius or degree Fahrenheit, but absolute temperature is measured in Kelvin. Then luminous intensity only has an SI unit, which is measured in candela. Lastly, in this video lesson, we are going to look at derived quantities. The word derived means obtained or gotten from something, just as furnitures are derived or gotten from wood or from timbers, or clothes are gotten from nylon or cotton. So also derived quantities here are those quantities that are obtained or they are gotten from the fundamental quantities, either by multiplication, division, or a combination of both. Now, what does that mean? We can get derived quantities either by multiplying fundamental quantities, by dividing fundamental quantities, or a combination means by multiplying and division of fundamental quantities. For example, we have what we call amount of electric charge. Now, amount of an electric charge is represented with Q. Now, Q is equal to IT, where I is electric current and T is time. Remember, both of them, electric current and time, they are fundamental quantities. So in this case, we have multiplied two fundamental quantities to obtain a derived quantity. So in this case, Q is a derived quantity. Also, for speed is referred to as, or is given as, distance over time. Distance is simply just a length between 2 points, is a length. So in essence, distance here is length and over time. Remember, length is a fundamental quantity and also time is a fundamental quantity. So in this case, we have divided two fundamental quantities, length and time, to obtain speed, and speed is a derived quantity. So also we have momentum, and momentum, the formula is mass times velocity, but when it is broken down, it becomes mass times displacement over time. Now, mass is a fundamental quantity. I'll mark it as F. Displacement is a form of distance, which is also length. This is also a fundamental quantity, and time is a fundamental quantity. So in this case, we have combined these fundamental quantities, mass, displacement, which is length, and then time, together to obtain momentum. So in this case, momentum is a derived quantity. So in essence, a combination of fundamental quantities, either by multiplication, either by division, or a combination of both, is what will give us derived quantities. Now there are some derived quantities that are here, and we'll just play with them to know their unit. Now there's one thing I want to tell you. Now remember, we have 7 fundamental quantities, which are mass, length, time, electric current. We have absolute temperature. We have amount of a substance, and then we have luminous intensity. Now out of these 7, take note of this, out of these 7, 3 are very important to you, hence we also call them the main fundamental quantities. So out of these 7, these first 3, mass, length, and time, are very, very important, or they are the most, or they are the main fundamental quantities. So take note of that, mass, length, time. In subsequent videos, we'll keep referring to what we call the MLT system. MLT, where M stands for mass, L stands for length, and T stands for time. So take note of this. Out of these 7 fundamental quantities, 3 are more basic, which are mass, length, and time. And also, let me add this to the video. Any quantity that is not among these 7, any quantity that is not among these 7, mass, length, time, electric current, absolute temperature, amount of a substance, and luminous intensity, any quantity in physics you come across that is not among these 7 is a derived quantities. Only these 7 quantities are fundamental. So if I give you a quantity, for example, volume as a quantity is not part of these 7, hence volume is a derived quantity. If you are given magnetic flux density is not part of this 7, hence magnetic flux density is a derived quantities. So we are going to play with these basic quantities we have here and derive their unit. So we are going to start with area. Now area, the formula for area is length times breadth. Length times breadth. So breadth is also a length. So this is length times length, because breadth is a length. If this is a room, this is a length, this is a breadth. They are both length. So length is measured in meter. Length is also measured in meter, and meter times meter is equal to meter square. So hence the unit for area is meter square. Volume is length times breadth times height. Again, they are all length times length times length. So length is measured in meter, the other length is measured in meter, and this is also measured in meter. So at the end of the day, your formula becomes meter cube. So the unit for volume is meter cube. For velocity, the formula for velocity is displacement over time. And displacement, like I said earlier, is a form of length. The shortest distance between 2 points is what we refer to as displacement. So it is like length over time, and length is measured in meter, time is measured in seconds. So the unit for this is meter per seconds, or there's another way we can present it in indices or in an index form. We write it as meter per seconds. So for acceleration, the formula for acceleration is velocity over time. So velocity is measured in meter per seconds over time, which is measured in seconds. So when we divide, we are going to get meter per second square. So in this case, unit is meter per second square, or if we apply it in index form, it's going to be ms raised to the power of -2, the same as meter per second square. Now for force is given as mass times acceleration. So mass is measured in kilogram times acceleration is measured in meter per second square. So when you multiply, you are going to end up getting kilogram meter per second square. So the unit for this is kilogram meter per second square. Now there's something you ought to know. When a formula is getting long, it is represented with other unit or names of scientists. So in this case, the unit for measuring force is what we also refer to as newtons. Newtons for short, or the symbol is N. Moving on, I thought of deriving the unit for acceleration again. So recall, acceleration is equal to velocity over time. Now for easier representation, I'm going to write it like this. Acceleration is equal to velocity divided by time. And recall that the unit for velocity is meter per seconds divided by time, which is measured in seconds. I'm going to write it as seconds over 1 to make it look like a fraction. Now in maths, you can't solve with this division. You can't solve fractions with that division. You must change that division to multiplication. And when you do that, whatever you have after this division sign, you are going to flip it. This one will go up and the s will come down. So your numerator comes down and the denominator will go up. So this will become 1 over s. So m times 1 is m, s times s is s squared. So that's why the unit for acceleration is meter per second square. Now recall that force from our derivation was kilogram meter per second square or newtons. So for energy, the formula for energy and work, they share the same formula. So the formula for both of them is force times distance. So they are measured, or the formula rather, is force times distance. Force times distance. And force from our calculation or from our derivation, the unit is kilogram meter per second square times distance, which is meter. So I'm going to expand this. It becomes kilogram meter over second square times meter. Now this meter here times this meter here will give us meter square. So it becomes kilogram meter square per second square. Now recall, this formula is getting bulky. Also, force is measured in Newton. Distance is measured in meter. So it becomes Newton meter. But there is a simpler unit for this, and the unit is measured after a scientist called joules. So that's why energy or work is measured in joules. So recall, the unit, or basically the SI for measuring newtons is, or for measuring force rather, is newtons. Then for measuring work is joules. Then for moment is just like work or energy done. So, or work rather, or energy. So moment is also force, but in this case the formula for this is times perpendicular distance. Perpendicular distance. So it's like force times, for short, this is symbol for perpendicular distance. Again, force is measured in Newton. Distance, whether it's called perpendicular, it's also a distance which is measured in meter. So n times m will give us nm. So the unit for this is newtons meter. Then for power, lastly, for power, the formula for power is work done or energy, because they have the same formula, work or energy over time. So to make it easier, I'm going to write it as power is equal to work divided by time, and work is measured in joules divided by time, which is measured in seconds. So for power, it's measured in joules per seconds or joules per seconds. Also, this unit is also named after a scientist, which is called watts. So the unit for measuring power is called watts, W. So this is some derived quantities, and there are a whole lot of others. So you now know the difference between a fundamental quantity and the derived quantities. So fundamental, they are simply the basic quantities. Derived, they are obtained from the fundamental either by multiplication, division, or a combination of both. Here are some practice questions on measurements and units, particularly on fundamental and derived quantities, taken from the JAMB past questions. And the first question is, which of the following is not a fundamental SI unit? Option A is meter, B is ampere, C is Kelvin, and D is radian. Now, taking a close look at the question says, which of the following is not, emphasis on the word not, a fundamental SI unit. So if it is not a fundamental SI unit, that means it is going to be a derived unit. So recall that we have 7 fundamental quantities which have their respective unit. So if we take a close look at option A, which is meter, meter is the unit for length, and length is a fundamental quantity, hence meter is a fundamental unit. Ampere is used to measure electric current, and electric current is a fundamental quantity, hence ampere is a fundamental unit. Also, Kelvin is used to measure absolute temperature, and absolute temperature is a fundamental quantity, hence Kelvin is a fundamental unit. So the answer to this question is option D, which is radian. Radian is used to measure angular distance, and angular distance is a derived quantity, hence radian is a derived unit. So the answer to question 1 is D. Now, a close look at the second question. It says, which of the following is a derived unit? A is kilogram. Kilogram is used to measure mass, and remember that mass is a fundamental quantity. Meter is used to measure length, and length is a fundamental quantity. Also, Kelvin is to measure absolute temperature. Hence, the answer to question 2 is Newton. Newton is a derived unit used to measure force, and force happens to be one of our derived quantity. Now, looking at question 3, which says, which of the following are derived quantity? Now, thrust is a type of force, so this is a type of force, and force is a derived quantity. So option 1 or Roman figure 1 is a derived quantity. Temperature is a fundamental quantity, so this is out of it. Area is a derived quantity, as we have looked at earlier, so Roman figure 2 is part of the derived quantity. Pressure is also a derived quantity, so pressure 3 is a derived, 4 so we have 1, 3 and 4. So the answer to this question is option C. So the exception is temperature, and temperature is a fundamental quantity. So Roman figure 1, thrust, is force, derived. Roman figure 3, area, is derived. Roman figure 4, pressure, is derived. Hence, answer to question 3 is Roman figure 1, Roman figure 3, and Roman figure 4. Roman figure 2 is a fundamental quantity. Now, let's take a close look at question 4, which says, which of the following is a fundamental unit? A is Newton, and Newton is used to measure force, which is derived. Watt is used to measure power, which is a derived quantity. Joules is used to measure energy or work, which is derived. But seconds is used to measure time, and time is a fundamental quantity. Hence, seconds is a fundamental unit. So the answer to this question is D. Moving on to question 5, the question says the internationally agreed system of units, in bracket SI, remember SI stands for an internationally agreed system of units, for the physical quantities are A says pound, feet and second, B grams, meter and second, C kilogram, meter and second, D centimeter, grams and seconds. Now, if you take a close look, the question says for physical measurement, and like I told you earlier, we have 7 fundamental quantities, but out of that 7, the first 3 are more basic, which are mass, length and time. And we measure mass with kilogram, length is measured in meter, and time is measured in seconds. So automatically our answer to question C is kilogram meter per seconds. The other options are other units, but our basic quantities, which are mass, length, and time, are best represented with option C, kilogram, meter, and second. Question 6 read, what is equivalent to A, Newton meter per seconds, B, kilogram meter square per second square, C, joules second, and D, Newton seconds. As we already know, watt is the unit for measuring power. And what is our formula for power? Power is either measured as work done or energy over time. So watt is measured, or is the unit for measuring power, watt. So energy or work done is calculated with force times distance. Force times distance over time. And force is measured with Newton times distance measured with meter over seconds. So if we multiply that and divide, we are going to end up getting Newton meter per seconds, which is synonymous to option A. So the equivalent to watt is Newton meter per seconds. So viewers, I hope you learned something from this particular video lesson. To my returning subscriber, thank you for being part of this channel, and if you are new here, I welcome you specially to this channel. You can do it to say thank you by clicking on the subscribe button so that you get notified whenever I release any new video. Till you get to see my next video, do have a wonderful time.